In this section, we're going to discuss sorting, which was introduced in the last section. A binary search is a fast way to search large amounts of data. The algorithm is more complicated, but the benefit is great in doing so. I finished the last section by saying binary searches depend on data being in sorted order. If data is not sorted, we are going to have to use some other scheme like a linear search. The binary search needing sorted data may demand more expense in the sorting than is worth it for the benefit. So we actually have to choose the right algorithm for the problem. If we're going to search one or two times, it doesn't make sense to sort all the data. Just do the searches. However, if we're going to search fairly frequently, it really pays off to sort the data and do binary searches. Obviously, careful study of the problem is required. Many simple algorithms exist for sorting data, but they are typically expensive, on order of n squared. Big O n squared means that the cost of the algorithm is in the order of n, which is the number of elements, squared. So it's obvious that the larger the number of elements, the cost becomes exponentially more expensive. There are ways of sorting that cost us n log n. And for anyone familiar with logs, you know that logs reduce big numbers to small ones. They're much faster, but again, much more complicated. We have to study the problem. It may prove that the sorting is reasonably done in n squared time for small data sets, and it may be the most efficient. Large data sets will always require something closer to n log n sorting time, simply so they'll finish in a reasonable amount of time. Two different sorts on order big O n squared. First, the selection sort. The idea of the selection sort is to find an element's place and put it in it first time. What we're going to do is start to look for the smallest element in the list of numbers. We're assuming an array. Find the smallest element and put it at index 0. What we do is iterate over the data using two loops. The outer loop is the position where the data element is to go. So when we're looking for the smallest element in the list, it's going to go at index 0. So our outer loop starts at index 0. It represents where to put the next piece of data. The inner loop would start at index 1 in this case and run all the way up to the end, looking for a number smaller than the one at index 0. We assume that the element at index 0 is the smallest. Chances are it is not, which means that inner loop will find an element that is smaller. And what we do when that happens is we swap them. So we put the new smallest value at index 0, and we continue the inner loop all the way to the end. So eventually, the smallest element found will be in index 0. Next, the outer loop increments to index 1. We look again for the smallest element in the remaining data. We assume that the element at index 1 is smallest. The inner loop starts at index 2 and goes all the way to the end. If it finds an element smaller than the element at index 1, swaps them, and on it goes. So this continues until we finally run off the end on the right, and every element is now in its correct location. An insertion sort works slightly differently. The insertion sort does not assume that we have the elements in their final position. What it assumes is that any elements we consider sorted are sorted relative to each other. So for example, if we had 1,000 elements and we only considered the first 10, the first 10 would be sorted relative to each other, and we would consider the other 990 elements unsorted. We start with the first element at index 0, and we consider it sorted relative to itself. Then we look at the next element and we determine, are these two elements sorted relative to each other? If so, great, we continue. If not, we swap them. So now we would have two elements in sorted order. Notice I've never said that the one on the left at index 0 is the smallest element in the list. It may not be. It probably will not be. But relative to its neighbor to the right at index 1, they are in the correct order. We increment to the next element, and then we arrange those 3 elements into the proper relative sort order, which means we may have to move the elements at index 0 or 1 or both to put the 3 elements in the correct order. And then the 4th element, again, we get the 4 elements in sort order, and then the 5th element, and on to the end. This approach may cause a lot of data movement. The order of the algorithm is, again, n squared, meaning that we are exponentially proportional to the number of elements. My gut feel is that an insertion sort always is more expensive than a selection sort. However, data scientists have discovered that insertion sorts tend to run faster in absolute time than selection sorts. It may be counterintuitive, but it's anecdotally true. The reason is that most data is in somewhat sorted order. So the insertion sort suddenly becomes faster. True algorithm analysis suggests that it either would be about the same as selection sort or perhaps more costly because of the data movement. Although not in this section, there is a sort called a merge sort. The merge sort is a radically different approach to sorting. Its order is n log n time. We will discuss this sort in the next section. The point here is it beats both selection and insertion sorts considerably.